All right, announcements plus where we are. So we are done with graded material in the class, aside from an optional homework that's due on Friday. I wrote that up, uploaded it on Friday, so you have an opportunity to work on that if you would like. Let me know if you have any questions. But other than that, what we're doing this week is we're just finishing up touching on graphs. We're going to talk about how to actually do a shortest path search that keeps track of weights rather than just the number of traversed edges. This algorithm shows up everywhere in computer science and everywhere on interview questions, which is why I'm going over it, because I am in the process of making a unit on interviewing. I think that is a very important skill to have in this field, and what people look for in this field are very different from what people look for in other fields. So generic interview tips and tricks don't work quite as well in computer science, so we have a lot more to think about. So a lot of that's going to be generally applicable, but it will especially be tailored toward those in this field. So we will probably start that either tomorrow or the next day, depending on how quickly we get through some of this content. So last time we talked about two different search types that we've brought up before with trees, but we talked about how do we do them with graphs, and they are the main focus of the assignment if you choose to do it. So we had depth first search that's going to just choose a path and go down that path and explore it. And the path it chooses is based on some natural order of whatever the node types the graph has in it. If they're strings, then we will always go to the first alphabetically and then look at those neighbors first alphabetically, look at those neighbors first alphabetically, until we get to a dead end, and then backtrack and look for the next closest to the beginning of the alphabet and go explore all the way down that path. So it looks very similar to the binary search tree version of depth first search. We found that it was very easy to retrieve the path as we did this because we were storing it inherently in the, since this call is recursive, we're storing it in the path of the recursion that we're in. So we can just store the path as we go. Basically, whenever we remove a recursive layer, we delete the last thing that we did. Whenever we add a recursive layer, we add the edge, the node that we're going to. And that tells us the path. By the time we find the solution, you just have to return the path that we're calculating as we go. We also talked about breadth first search, which just looks around in a kind of an ever-growing circle out from the source node. We found that breadth first search finds shorter paths than depth first search, but we had a significant memory requirement as we have to keep track of every node that's anywhere on what we call the frontier. It's adjacent to some node that we visited before. So we looked at pseudocode for this. It was very quick, easy pseudocode, and we found that it's much harder to store the sequence of nodes that we visited because we have to have back pointers. We need to store where we came from when we explore those new nodes. And that will return the associated path. We know we get the shortest path in terms of number of edges, but if those edges have weights, then what we return is not guaranteed to be optimal. So we need some way of calculating the weight that we've seen as we go and optimizing the path of least weight cost, not just the number of edges that we traversed. Questions on depth first search, breadth first search, pros and cons of each, and what's still left to do. Situation where neither of these are good enough. We talked about their associated runtimes as well. They run in big O, the size of E plus the size of E. We're going to visit each vertex at most once. We're going to traverse each edge at most once. So that gets us that B plus E runtime. All right, now we're going to start looking at some applications. So here are some connections within Washington State. We will say that these are I don't know, it doesn't really matter what they are, we'll say that they're roads. If these are the only roads that existed, what would the shortest way to get from Seattle to Pullman be? We have guesses, but we don't really have edge weights here, so we kind of have to just do something visually.
Seattle, Spokane, go 1 inches.
Very well could be. Yeah, probably Seattle, Cleo, Moses Lake, Richland, Pullman. That probably has the absolute shortest path. What about the fastest way? Straight down I-90, depending on what rocket car you have. Well, let's pretend that I-90 is an autobahn. And there's no speed limit, just a long I-90, you can go as fast as you can dream, and you're in some kind of rocket propelled car. Then maybe there's a difference between the shortest way and the fastest way, because there may be a long stretch of that path that you could take that would be significantly faster. How do we know the shortest way and the fastest way? Algorithmically. How would we have to figure that out? You'd either need weights, if it were just in terms of the number of edges, what are the shortest number of edges to traverse to get to Poland? What would we want to use?
Well, there's so many ways to get there with 4 inches, so how would you differentiate?
There's one way to get there with 3 edges. Yeah, Seattle to Wenatchee to Spokane to Pullman is 3 edges. What algorithm would identify that?
One that's counting the depth, no, or the height.
The one that's counting the number of edges traversed, basically, we explore everywhere with 1 edge, everywhere with 2 edges, everywhere with 3 edges, we find that we unveil Pullman as we were searching on that 3 edge path, so that's breadth first search, that does the close to us, a little bit farther away, a little bit farther away in terms of number of edges. But again, as soon as there are weights on there, everything's out the window. So now we're going to say these are phone exchanges. And now imagine that the phone exchange is a node. So to communicate from Seattle to Pullman, we have to go through one of these. We have to basically relay the phone message to any node to try to contact Pullman. So can Seattle talk to Pullman if Wenatchee's phone exchange goes down?
Yes.
Yes. We could use any searching algorithm to answer that question. We just need to know, is there a path from Seattle to Pullman? Doesn't matter how long it is. So if we cannot explore Wenatchee, is there some other node that we can go through, or sequence of nodes we can go through to get to Pullman? Depth first search or breadth first search could answer that for us. If Tacoma's phone exchange goes down, can Olympia talk to Spokane? How would we know that algorithmically? You could think of it that way. We probably need to still do some kind of breadth first search or depth first search to be able to say, is Spokane still reachable from Olympia? A breadth first search keeps track of a queue. If that queue ever becomes empty, that means that there's no work that we can do from there. There's no work we can do. So if that's the case and Tacoma's goes down, we would explore Olympia and Enumclaw and Vancouver, and then queue would be empty. We never saw Spokane, so we know there's no way to reach Spokane if Tacoma is an unreachable vertex. So you can imagine that this is one such graph. These are some of the questions we get asked about it. How about this? This is downtown Seattle. So if we are asked 3rd and Pine, and we want to get to 1st and University, and this is the associated metro graph. Can we go from 3rd and Pine to 1st and University?
Yeah, you have to go either
all the way down to First and Pine and then to First and University, or you have to go all the way to Third and Seneca, and then to First and Seneca. To First and University.
Yeah, so there are multiple ways to get there, but we know this from our searches because eventually we would reveal the destination as somewhere that is reachable. Doesn't really matter how long it takes us to get there, the idea is that we would uncover it. Could we get to Fourth and Seneca?
From Third and Pine.
Or Third and Pine, yeah. We cannot. There are edges out of Fourth and Seneca, but no edge into, so we can't actually get there by measuring. So this is usually how a graph search is done. You will implement something like a breadth first search or a depth first search, depending on your memory constraints and whether you need the shortest path in terms of number of edges when you do it. And if you don't reveal the destination, then it's unreachable. So the reachability question is an important one. There are a couple of other search algorithms that you may explore in a little bit more detail if you take something like an artificial intelligence class. So the first one to be aware of is iterative deepening. Basically, we're going to use depth first search, but we're going to keep track of the depth that the depth first search is in and not allow it to go past a certain depth. Can anyone think of why we might want to do that? Basically, if we don't find a solution, we can start over, increment K and research. What's the value of this? Why would we ever care to do this?
Probably like minimizes search line, just in case it's at the upper echelon.
Yeah, so depth first search had a very big pro, memory. This is the equivalent of a breadth first search using depth first search. So we return the shallowest solution using depth first search that we would have found using breadth first search, but we get depth first search's memory, beautiful linear memory. The issue is we're going to be redoing some work. If k equals 3 and we look 3 stations away and don't find the solution, then we have to research all of those nodes as we search up to 4 stations away. Then we have to redo all of that work as we search up to 5 stations away. So as always, there's a memory trade-off in computer science. So iterative deepening is saying we're going to get the best of both depth first search and breadth first search, but the cost for that is time. It's not in a different order of time, but it will be longer. So finds the shortest path, uses less memory, repeats some work, but that time penalty is actually minor compared to the amount of space savings that you get. So we find that this is often done in practice rather than using breadth first search. We'll use iterative deepening if we want to find, if we don't know how deep the query is going to be and we have a large graph. There are other kinds of search algorithms that are really useful if you know where the destination is and you're not just trying to search around blindly for the destination, but you actually know something like, I know that as the crow flies, the destination is 70 miles that way. I just don't know if there's a direct road there. You can start to explore around and try to find the route to that destination if you know where the destination is, as long as you have a good heuristic. A good way of approximating how far you have left to go. If you have some way of doing that, you can implement what we call A star, which is the optimal pathfinding algorithm for just about anything where you know where the destination is. So it's used very much in games. And I think I may have said this in here before, but there's nothing scarier than being chased by A star. It is so perfect that there's nothing, but the best that you can do is keep it how far it is behind you. As soon as you make any suboptimality, it's closer. Any suboptimality, it's closer. Scariest thing ever. I had my game dev students make something that needed pathfinding in it, and a lot of students were just like, I'm just gonna make A star. One of them made this really large, really grotesque baby Yoda and had it chase you through a maze. And man, when it found you, it was so scary to just see this thing shambling at your speed, optimally behind you, knowing it was just a matter of time until it caught you.
Is there any way to disrupt something like that? Like to.
You have to be able to control things like where they can and can't go. So like you open a door, you close it. Now A star has to research and find a way around that door. So there was a little bit of that in the game. One of the games that was designed
Can it
was,
do it if it can open the door though? Like it knows how to open the door, does that make it not disruptive?
yeah,
Oh,
or maybe you can give an extra amount of time. It takes 5 seconds for it to open the door, and that gives you 5 seconds of leeway to increase your chasing
how
distance.
does it know where you're at? Like, what is it searching for? Exactly, it's like, cause it
It's
doesn't
searching
search
for a path to get to your position. So if it knows where you are,
So how, is there a way to prevent it from knowing where you are?
line of sight, basically, it knows where you are because it can see you.
That has like a radius.
Yeah, either a radius or vision, of whether there's light, you can query how lit up is this? Is there a threshold of what's dark or how far you can see in particular darkness situations?
Okay, that's like a lot of how Explorer games. work.
Yeah. Yep. A star is scary though, if you give it full information. One of the best games that was designed, sorry, this is a little bit of a sidetrack, but I love it so much. I love any opportunity for people to be clever in computer science. And this group of students came up with a game where you're at a picnic and there is an ant spawn location and they use A star to reach your picnic. And you end up with things like you have a single square cylinder, whatever we call those, log. You can put that down and force the ants to go around it. And you can pick it up and put it down. But they start to branch and go around it. So where you place that and when you pick up and put it down, you have a certain amount of time that you need to protect your picnic. So you're basically learning how to get around A star when A star is hunting your picnic. And then later levels have multiple ant spawn points and then multiple logs, so you're trying to like bring them together into one thing that you can effectively block off. And they actually did a great job of making a puzzle game out of A star, and that was really cool to see. So yeah, the more you understand these algorithms, the more you can turn them into interesting outcomes where interacting with them creates some kind of puzzle or some kind of horror experience, or yeah, games underneath the hood are a lot of algorithmic work. Where you understand the algorithm and you understand that there's some fun interacting with the algorithm if you give the human some superpower. Algorithms are frighteningly efficient. Anyway, so the most common search that we see in computer science is a weighted shortest path. So how do we find the shortest path on a weighted graph? There's no way to know that the path length is gonna be the shortest path cost or the lowest path cost. There's no way to know that. We talked that breadth first search can find the minimum path length in size of V plus size of V. But let's get a sense here. What's an example of a graph where breadth first search would struggle to find the minimum path cost? If I asked you to design a graph that was as difficult as possible for breadth first search to find a solution.
Probably it was square and put everything towards the bottom right.
Yeah. Yeah, so here's an example of something that breadth first search would really struggle with. The shortest path length to the goal is one edge. We can get there with cost 500 in one step. We can get there with cost 400 if we take 3, 4 edges. So something like this is really difficult, where breadth first search will terminate, but not with the correct answer. And depth first search will terminate not with the correct answer if it chooses the 500 first. If it chooses the 100 first, we're good. But there's no guarantee that we can find that path every time. One thing that the shortest path algorithm does not allow, and I hinted to this earlier in the slides, was that we cannot have negative edge weights. If we have negative edge weights, then the guarantees we get out of this algorithm are for nothing. Especially something like a negative weight cycle. So here's an example of a graph. We're trying to get from A to D. What is the least cost path from A to D? You can revisit vertices. Yeah. A, B, C, B, C, B, C, B, C, B, C, B, C. There's no reason we ever want to actually finish that and go to D. You're just gonna get stuck in this BC loop that creates an effective negative infinity weight between A and D. There's no way for a shortest path algorithm to terminate on this. Because regardless of what weight we currently have, we can get a lower weight if we go through this negative cycle, negative weight cycle. So same thing from B to D. In general, we're just not going to allow negative edge weights. There is a way to get around this, but it requires a much more complicated algorithm that I have no idea if algorithms actually covers. If not, some kind of advanced algorithms course would cover it, but just note that there is a way to get around it. It's just way more complicated. So if you don't have to consider it, you shouldn't consider it. Don't use the expensive algorithm on a not expensive problem. So any graph without negative edge weights, this algorithm, Dijkstra's algorithm, will work on. So one thing to note as we start explaining Dijkstra's is it does look a lot like breadth first search. In fact, it's basically breadth first search adapted to handle weights. With breadth first search, we used a queue. Instead, with Dijkstra's algorithm, we're going to use a priority queue. And a priority queue is implemented using a heap, which is why we covered heaps before covering this. Because we are going to be storing which edge we want to explore and which vertex we want to explore via that edge with a priority queue. We want to figure out, of those that we can get to, what is the cheapest one that we can find so far. And that would be stored at the root of a heap. So we're going to have a set of, we're going to call it visited, whether a node is visited or not, or explored or not. We want to find the shortest path from an initial vertex to every other node as we calculate this idea of the shortest path to that node. We're going to be storing this concept of a best distance or shortest distance so far as we do this exploration. It's not guaranteed to be optimal until we visit the node. Once we visit the node, we found the shortest path to that. So yeah, once we visit a node or expand a node, either one of those are fine terminology. Then the optimal path to that node has been calculated. By the time we don't have any further vertices to go visit, we will have found the shortest path from the source to that node. So this is again a one-to-many search. Just like with breadth first search, we found the shortest path to every node. There's a single source, and with one iteration of Dijkstra's algorithm, we can calculate the shortest path to every other vertex in the graph. But it's just from that one source. As soon as we have a different source, that information doesn't help us. All right, so here's Dijkstra's in its beautiful glory. So the start node, the place that we're choosing as our source, has cost 0 because we're already there. We're at the source when we begin. All other nodes are initialized to have some cost infinity. If you're using integers, you can use integer.max value. You can use anything that represents the concept of infinity, since we can't usually store infinity If you store the edge weights as doubles, there is a double dot infinity in Java that you can use. At every step of this algorithm, inside of the, whenever we go into the innermost loop, we're going to pick the closest unknown vertex. So all of the vertices that we have expanded or explored are going to be known. Those that have a connection to something that is known is unknown. So we're going to be looking at all of the neighbors of all of the nodes that we have visited. And we want to find which is the cheapest to get from any node that we have, or through any node that we have visited to that node. Then we add it to a cloud of known vertices. When we expand that node, we're going to look at all paths out of that node. Some of those will lead to vertices that we've explored before, and some of them will lead to new vertices. So we're going to be updating, one, the list of vertices on the cloud if we find a new node that is adjacent to a node that we're visiting. And we're going to be looking for edges that connect to vertices that we do know and see if that path is shorter. If we can get a shorter path going through this newly explored node, then we update the best path that we have to that node to be through a new node that we visited. I can't just explain this in words and have it make sense, so I have 3 examples that we're going to go through. The first I'll just guide you through and have some where you can get to practice. But here's kind of a visual of the cloud. We've explored nodes A, B, C, and D, and now we want to find the shortest path to E and F. Those are now on the horizon, you could say. These are 2 vertices that are neighbors of nodes that we visited, and G and H are still currently unreachable because they're not a neighbor to something in the cloud. As we explore E or F, we will start to be able to explore those nodes G and H that are still outside of the scope of the cloud. By the time the cloud envelops the entire graph, then we will know the shortest path from A to every other. So here's pseudocode before we get started. We're going to go through each vertex that is not the source, and we're going to initialize it, setting its cost to infinity and the fact that it is not yet known. The source, on the other hand, has cost 0, and it starts out as known. It's part of the cloud. So we then need to say, what are all of the nodes that we can get to from our source? We're going to add them to the priority queue with weight equal to the cost of getting to that node from the source. So let's just give you the example here. This is kind of the table we want to produce. We're going to use this same graph for example number 1. So we start with our initialization procedure. The cost of A is 0 because that is the source. The cost of everything else is infinity. We then say that A is known or is visited, and we have paths from A to B and C and D. So we need to store the backtrack pointer, kind of like we did in breadth first search. We say B and C and D are now on the frontier. They're somewhere that we could go explore, and if we do go explore them, it will be through node A, which will lead us to the best cost for how to get to B and C and D. Everything here makes sense so far?
The reason you do it less than or equal to rather than exactly.
Because we don't know if that's the best path. So for instance, let's say this 2 were flipped.
So this algorithm like lives in a state of permanent doubt about itself.
Until it adds it to the frontier. The best way to get to A is through A, cost 0.
So we're in a stage where we're projecting into the future basically.
Yeah, we're saying, where can we get with 1 step from A? If this were 1 and this were 2, there would be a 2-step way to get to D that was better than the 1-step way to get to D. So we say less than or equal to 4, because we may still find a better path as we expand and explore paths of longer lengths. So we found a way. We found a way to get to that vertex. It may be the best, it may not. We don't know. We haven't proven it yet. So we use the priority queue now to pull out, it's a min heap. We're gonna pull out the lowest cost from the frontier. The frontier contains 1, 2, 3 possibilities. We want to pull out the node with the cheapest cost. So that's C. So the next thing we're going to make known is C. So now that we've expanded C, this less than or equal to 1 becomes 1. Because we have explored C, and now we have two things that we need to do. We need to check, one, well, it comes from all the out vertices from C. We see that from C, we can get to A with cost 9. So we ask, is 1, the cost of getting to C plus 9, so 10, better than the already known cost to get to A? Is 10 less than 0? No, so we're not going to update A. There's another new out vertex to E. So we look at E and we see that we're gonna take the 1, the cost to get to C, plus the edge length 11 to get to E. And previously that cost had been infinity. Is 12 less than infinity? Answer is yes. So we're going to update our next best way to get to E, saying that it's going to come through C. And if we look back at C, the way we got to C was through A. So we're keeping track of every possible backtrack that we could use. Once we say, if the destination node were E, we wanted to know how did we get there, we would follow the C back to the A, so it was A, C, E, and that was the way that we got to E. Everything from this step makes sense? So the next one, we're gonna go through the frontier, and we find that the next best is F. Sorry, is B. B had cost 2, so now we've cemented the cost B. We look at all the out edges from here, we can now add F at total cost 4, the 2 to get to B plus the edge weight from B to F. And that goes back through B. There's also a way to get to E. 2 plus 10 is not better than 12, so we're not going to make any change. Note that you could make this change. Basically, now we have 2 equivalent paths of getting to E. You can either go through B or through C. Whether you replace this with B or leave it as C, doesn't matter as long as you're consistent. All right, what do we do next? What is the next one we're going to visit? That's high. So the minimum cost is either D or F. Again, it doesn't matter which one of these you do, as long as you're consistent. So you can explore either one. We're gonna go in alphabetical order and tackle D next. So updates that we make, we solidify this 4 as the best way to get to D, because now we've explored everything that has an in edge to that, with the exception of this one. Is there any way that this could be less than 4? Why do we know for sure that the best way to get to D is 4 when we haven't explored this edge? Yeah, if there were a shorter path through E, we would have found it already. By the fact that we're exploring this was the least cost that was here. This weight would have to be negative in order to get to D and have a shorter path than the one we've already found, which is why we don't allow negative weights in the graph. If we did allow negative weights, then there'd be no way to guarantee when you explore something that it's the lowest cost way to actually get there. We would lose that guarantee. So we update nothing since there are no new out edges of D that we haven't explored before. So nothing gets updated. Now we pull out the next one from the heap. We're going to go explore F. As we explore F, we find a new way to H that is less than infinity. Our back pointer is going to point at F as the way that we got this cost of 7. We took the cost to get to F plus the edge weight from F to H, that gives us the 7. There are no other out edges from F. So now we go through and pull out the minimum from our heap, which is this 7. We still haven't gotten around to exploring this E. It's been in there for a while, but we keep finding new, better ways to get around the graph. So you see that large edge weights get caught in the system for a long time before they're explored. Which is good, that is behavior that we want. So we explore the H and find that there's a way to get to G from there. It's the first time we're seeing G. We then loop around, explore G, as 8 is still less than 12. And going through G, we actually found a better way to E. So we've been sitting here waiting, saying the best way to get to E is 12, either through C or through B. But if you go B, F, H, G, E, you actually have a better way to get there. And so now we're actually seeing that as the cost to get to G, 8, via some path, plus the edge weight from G to E, gives us 11, which is less than 12. So we're going to update this cost, giving us a back pointer of G. We got to G through H, we got to H through F, we got to F through B, and we got to B through A. So that tells us the path that we use to get there so that we can reconstruct it, as long as we have this path column. So that's why that's important to store in Dijkstra's. And finally, we go to expand E. And the reason we waited so long was just in case we found a faster, better path, which we did. So now that we have nothing left to expand, our priority queue is empty, we're done. We found the shortest path by edge weight from A to every other vertex via this process. Questions on Dijkstra's algorithm? Does the concept make sense? Process make sense? We don't really have a ton of time here. We can just say that when we visit a vertex, we know for sure the shortest path from the starting vertex to that vertex. We know what path that is by following the back pointers. When we don't yet know the shortest path to a vertex, we may still find another shorter path that we find in some later iteration of that. So we'll stop there for today and we'll come back tomorrow with, we'll probably go back through this last example and give you a new one for practice.
Starting Wednesday, so doing the sort of review.
I'm thinking we might start it tomorrow. I think there's not quite 50 minutes worth of material left here, so we'll probably start. Yeah, I am not those of them. Luckily, there will be no actual. Unless you're submitting the option assignment, in which case you need them.